Okay, in this video we're going to work a problem that requires us to apply both principles of static equilibrium that we've done before, but we're also going to fold in the idea of using moments. Okay, so the problem statement says to find the reaction forces at points A and B. Alright, so we get started by making a free body diagram. So let's make a free body diagram of the beam. Okay, so there's the beam. And at this point we need to put the static or model the forces at point A, and point A is connected with a pin. Alright, so because it's connected with a pin, we have the force of A being in the Y direction and in the X direction because it's a pin. B, on the other hand, is just a balancing point. You could think of it as equivalent to a roller. And so we're just going to see a vertical direction force for the force at point B. Okay, and then we have the 180 pound force at the end of the beam. Okay, and so the free body diagram, you also would put in the distances, 6 feet and 10 feet. And there we go, there's our free body diagram. Okay. Let's see, maybe get a little more space here. Okay, so from there, we ask, well, what's our next step? And typically what we need to do is sum of forces in the x direction equals 0, and we need a coordinate system, so we're going to say x is positive going this way, and sum of forces in the y direction equals 0, okay, where this is up is positive. But then we're going to add another equation where we can do the sum of moments, okay, about any point. Okay, so we have a couple of points already labeled on the diagram, A and B. Okay, so sum of moments about any point, we get to choose that point. All right, and typically we're going to make counterclockwise be positive. So those are the principles that we're applying. Okay, so I look here and I notice, well, let's do sum of forces in the x direction, and I look at the diagram, there's only one force in the x direction, so let me just break this out. Sum of forces in the x direction equals 0. What we have is FAX, and there's no other x direction forces, so that means FAX is equal to 0. Alright, so we're feeling pretty good about that right off the bat. We've solved one of these components of the force at point A. Alright, next we're going to look at sum of forces in the y direction equal to 0. And I'm looking here and I see FAY going up, FB going up, and 180 coming down. Alright, so I just sum those in the appropriate directions. So FAY plus FB minus 180 equals 0. Okay, so at this point I have two equations and three unknowns. Well, we know FAX, so one equation now that involves two unknowns. Alright, so it looks like I'm going to need another equation. Okay, and I can get this by using the sum of moments equal to 0. Okay, so if an object is not rotating, all the moments at any point, you calculate the moments about any point, and it should be 0. Alright, so one of the tricks is to carefully choose which point you want to sum moments about. Alright, in this problem, it's not going to matter that much. Alright, so we could just choose point A or we could choose point B. We could choose another point and we'd get another equation, but generally you do a little less work if you're clever about how you choose the points. Okay, so what we're going to do is we're going to do a couple of examples of this. Let's do the sum of moments about point B equals 0. All right, so B is our moment, our choice. We're going to sum all the moments about point B. All right, so I'm looking at point B, and I see from point B 1, 2, 3, 4, 5. Well, it says 6 units away is FA. All right, and so the perpendicular distance between point B and the force in the y direction is 6, and so our moment would be 6 times FAY, all right? And the only question then is which direction is the rotation. So if I'm pinned at point B, looking here, do you see, let me just mark over it. I'll use a different color. Point B, here's the moment arm, okay? If I move FA in this direction, it's going to cause a rotation to be this way. Okay, so that's clockwise, so that would be a negative sign. Okay, so I'm going to undo those marks. So this needs a minus sign, okay, because this rotation is clockwise. So minus FAY, all right, and then there's no moment generated at force B through point B because it works on a line of action through point B. So let me highlight what I'm talking about here. So I look at FB, this force B, it goes through that point. So the moment arm is 0. So 0 times anything is 0. There's no moment generated from the force applied at the point B. That's part of the trick, right? You do that so that the variable FB will drop out of the equation. Okay, and so finally what we have is the force at 180. Okay, so 180. And I'm looking at that distance is 10, the perpendicular distance is 10. 10 times 180 is the moment that's generated, and this time it's also going to be in a clockwise direction. So this is a minus sign, minus 10 times 180. Okay, so I'm looking now at what I have. You know, that's part of the process. You write equations, you take a look, you assess what do you do next. Okay, and I'm liking this because I see FAY as an equation by itself. All right, so FAY, you know, I know everything else in that equation, so I have minus 6 FAY is moving the 10 times 180 to the other side of the equation. I get FAY equals minus, okay, minus 10 times 180 over 6. So I think that would be 180 over 6 is 30, so minus 300 pound force. Okay, so what's the significance of the minus sign? Okay, well, we had said the reaction force would be, we'd drawn it in a direction. I just drew it up. I didn't really think much about it. I just drew it in the up direction. So that means FAY actually is 300 pound force working in the down direction. Okay. All right, so once I know that, I can go back and I look at this equation. All right, so what I know then is FAY is minus 300. So plugging into this equation, minus 300 plus FB minus 180 equals 0. So that lets me solve for FB. So that would be 480 pound force. Since that's a positive number, that's operating in the direction that we're showing, which is up. Okay? All right, so that's the solution. Let's, though, continue to play around with this a little bit and talk about what if I generated the moment or written the moment equation at a different point. Okay, so let's write it at point A instead of point B. Okay, so I'll go back and look. If I'd have done that, okay, writing the sum of moments at point A, I have FB generating a moment. It would be 6 times FB, and it would be counterclockwise. All right, so that would make that torque or that moment positive. Okay, so 6 FB. All right, then I also have 16 is the length of the moment arm. 16 times 180, and this would generate a clockwise rotation, so 16 times 180. Since it's clockwise, that would get a minus sign. So you see, that's the sum of moments about point A, and that gives me a different equation. Okay, so I solve for FB, and that should give me the same number, 480 pound force. Okay, so I chose either point A or point B, but you could choose some random point in the middle. All right, it's just that if you do that, you're going to get none of the variables are going to drop out. So notice when I use sum of moments about point A, I didn't even talk to you about why did I ignore that? Well, it's because it's along the line of action of A. And so I don't even pay attention to any forces that go through the point A. All right, so if I'd have written this sum of forces equation around any other point, I could have made it work, but it would have generated just a tiny bit more work. Okay, so there's a quick example. We'll do more of these.